All right. Yeah, that's another live stream, spontaneous one. First of all, I wanted to thank everyone for being so supporting this week with the situation here. I really appreciate it. It's helpful, and I really enjoy seeing what you create with Walkway Simulator. It makes me so happy. And while preparing for the next Pi Pico Deep Dive class, I found few interesting bugs in the emulator. So um, I wanted to, just get rid of those bugs and also show you some cool tool I worked on yesterday, which will probably help us find and eliminate many more such bugs. So let me share my screen. We can be able to see my screen. I don't know if anyone is watching the live stream that haven't been planned. It's totally spontaneous, but worst case, you can also always watch recording. Okay, so let's start by taking a look at. Oh, they're so messy here. Let's close a few tabs for starters. All those we no longer need. How to set take a look at later. So yeah, so the plan for today is just close all these tabs first of all, just to go over this. Hey Steve, great to see you here. Thank you for playing with the microphone. It was really cool to see things that you come up with. So yeah, we have a bunch of bugs that I found, and we are going to go over them, explain them, and fix them. I think these like 3 new bugs are happened. I found them since the last spontaneous live stream, and also one we compare the behavior of. We ran our tests against the silicon, and we found some differences. And hey, Tomasz, good to see you again. Good to see you here again. And one more thing I would like to note is that Valerio also sent 2 pull requests to just make the tests prettier. So we added all those. I think we reviewed it in the sort of broken live stream earlier this week. But yeah, Tomasz has just added all those opcode encoding functions, which is really nice to tidy up the tests. All right, so let's get started with the bugs. And when we finish with the bugs, we will try to get MicroPython to run in the emulator, just because I really want it to happen. Hey, ProteusNet, nice to meet you. Where are you from, by the way? I have seen your name here in the past as well. Okay, so let's get started with this one because it's the oldest. And I think this one is we found it in the last spontaneous session where we ran all our tests against the simulator, and yeah, and Valerio also noted that he found those tests that involve SP and they failed. And you can see that in our test, like this is the test that we ran against the actual silicon, and you can see that we had this one probably shouldn't have failed. It seems like a bug in the testing framework, but you can see that in this case, like add R1 SP4, we expected 85, what we get from the emulator, but we got 84. And there are like a bunch of other interesting failures, like this one, and interesting. Yeah, I don't know. I expected false here. We'll have to check this out. ADR1IP. But yeah, you can see the same thing. I think happens here, where the expected and the received number differ by 1 bit. So there is definitely some bug here. and I looked at the datasheet and I found that here now, yeah. So using this R13, which is the stack pointer as well as a register, you can see that this lower bit should always be 0 or preserved. I don't know what preserved means, but basically reading from them returns 0. So cool to see that you are from Australia. So yeah, so let's fix that. I mean, it's an easy fix, just making sure whenever we write to this register stack pointer, those bits should be 0. So let's first fix those tests that are like those two tests. We will have the same spec. So this one. So yeah. So in this case, yeah, you can see the test assert that the lower byte is like the lower bit, the LSB is set, but we know it should be clear according to the datasheet. So let's first fix the test. And then we have another one, which is the second one, which this one. So this test is actually setting SP incorrectly. So I'm not sure. I think in real life that should probably never happen. I mean, I think we can always add a line number. So in this case, we'll just fix the test, I guess, because this situation is invalid. Maybe we should also fix like the debugger or like something like that. That whenever we write to no, we'll just fix the test. So basically, 454 and 54. And then we'll have the same result on the silicon as well, because this is invalid. And do we have anything else involving SP? Maybe it I'm not sure. And no, in this case, SP. Cool. So I'm not sure what's the problem here. Oh, I know. I think I know what's the problem here. We are just writing uint8 here into this address. The thing is, there might be some garbage, so this could be the reason this failed. I guess similar to this is probably similar to this. Yeah. Yeah, and nothing else involving SP. So I think here, yeah. So that should fix 2 out of the 8 failed tests we had in the last stream, and this one is probably false positive, and we still have to check those others as well. We'll get to that. But first of all, let's fix this tests. This one, want whenever we add registers, make sure that SP, or let's just, go to the code and see in which cases we update SP. Yeah. So first of all, we can always here when we set SP, and I don't know if there is like other places we access this register directly. Let's see. No, this is the only place where we do it in the code, so it should be easy. So we should just clear the lowest bits. That should break, and no, it's still not print. Let's see why. So it usually do open the side up at 40. Oh. Yeah. Yes. Action date. Yeah. Register. Yeah. So in this case, our yeah, nation register could be SP. SP. Then we have a problem. So yeah, we can. You can see we already got this thing where we check if it's a PC register. Then we do one thing. Otherwise, we do another thing. I think should probably split it into three cases. So in case we already have this test that checks if it's not the SP or like the PC. Oh, thanks, Valerio. Good to see you as well. So in case this is not SP or PC, then we can just copy the result. Else, if this is PC, then we have this logic, which just clearing this bit, and else RDN is SP register, then just we don't update the flags and we need to clear the two lower bits. Yeah, let's actually change the test so it fails even if we have this problem. So let's say we are adding 13x, then here both bits, test will pass. Great. So that should probably fix that bug with SP. We can see that now the test, I mean, we haven't run it on the actual silicon yet, but the modified one, but we can see that if we go back for a moment to the original one, it's green, so it's good. And I'm thinking if there are any other instructions that may write to SP. Most instruction can only write to the lower 8 registers, but I think move can also like write to, yeah, the destination register can be, RD can be also like as. So let's add another test for move just to make sure that we don't miss that as well. So I don't know if you can actually move something SP. Let's check out what the datasheet about this. Yeah, so no worries. Where's Valerio? Cool. Move. Where is move? Here we go. And there is move. Move. Me move the mic a bit closer so you can hear me better. This. Okay. Maybe now you can even hear me better. And move. Move. Okay. Move is actually. Oops, the instruction. But we have, oh, move register. That was the one I was looking for. So apparently you can't move to SP if I'm not mistaken, because the destination register is. So how do you? Is there any way? There must be a way to address the higher registers. another encoding for move. RM. Oh, yeah, this dbit. Yeah, okay, cool. So yeah, now it makes sense. The register is SPC, provided S is specified with S. Probably the set flags. Yeah. Interesting. Doesn't seem like we are updating the flags in move. Should we? Yeah, I think we have a couple of bugs here because first of all, it seems like It seems like if the destination is PC, then we should also use this ALU write PC instead of just writing to it normally. Then yeah, should update the flags only if E isn't set. So there are like two encoding friends, like all zeros, so not not this. I think this encoding is actually like implemented by a different instruction or something like that. Can't be that we didn't implement it, because I think so. It could be that this encoding isn't used. Move and update flags. That could be. Let's try to check out our assembler opcode move. So yeah. Oh, moves reg. That's the that's move and that's moves. So we are using it. Moves, and there is like for the register. So let's see what is implementing this. Something should be green. Something should execute when this test runs. Okay, so this is covered by LSRS and it takes care of updating the flags, and obviously here like the register can be PC or SP, so I think we don't care about it. Cool, so we only have this move, and then so this encoding, and then in this case we don't set the flags anyway. So all we got to do is just to make sure that first of all, if we are writing to PC, then we are doing this ALU write PC, and if we are writing to SP, we are keeping this SP bits, lower SP bits clear. So let's start by like adding a test case. Or it should keep lower bits here and computing instruction. Right, so we are going to move SP, say R5, and R5 will be 53, and then we expect SP to be 50, and doesn't seem to have done. Focus on this test. Move register. Move. Moves reg. Move. Okay, yeah. Now move it up, just above moves. Okay. And yeah, now we have a failing test case. Great, and we can see like it gets into this, and obviously we should here also let's do this. So if it's PC registered and the registers or this dot c equals plus equals, oh, that's the source register nation. Yeah, wait a sec, maybe we have another bug here. There was like this table with the cycles. Find it if I will. So moves was like this. How many cycles it take? I think we have another small bug here. Nothing too serious. Move RDRM. Move target is PC. Then the cycles should be increased by 1. So let's take care of this. First of all, if its target is this, then let's have let value equals, then if source c, then it's plus 2. Next instruction, I guess, or yeah, that should be plus 2. And then else if rd equals sp registered, and just value clear those lowest bits. Okay, so this should, yeah, this move case. And finally, wanted to see what does ALU write PC does here. Goes branch write PC, goes to branch 2, and it clears the lower bit, and branch 2 just set PC to address. So the only thing we need to do here is just clear that lowest bit case. So let's another test case for that for a moment, where bit P when moving R5, and then we expect PC to have this lower bit clear. Registers.c to have the lower bit clear, and this should be red. Yeah, and now if we enable this small fix, then it should be green, hopefully. Still red though. Why is that? Filter, so oh yeah, PC, not SP. Okay, this is green now, and without this fix, be red. Yes, great. All right, so I think with that we probably there might be another place where we can have a register that is like an instruction or something that can write directly to this dot registers, and in most cases it's just one of the 7 lowest registers, but by 8 lowest registers with this bitwise OR. But if you spot another case, then let me know, fix this. Otherwise I think we are pretty good with this one, and let's commit this. And one less bug to worry about. Ifs before we commit. So yeah, like the test. This is in clearing it when setting it, and there's like fixing add, and move. You know what? Before committing, let's just try to run the tests against the silicon one more time. So just need to remind myself how we did it last time. I think we have to set an environment variable. Instructions spec, like the function, I think, yeah, GDB, test GDB server. So we need to, I think that's the syntax to do it. And if I'm not mistaken, DNS was slow. So let's put the IP address. Oh, great. This is like the IPv6. Oh, maybe it will work. Who knows? Let's try that. We got nothing to lose, right? And let's run the tests again. Test. See if we get better results. Less than 8 failing tests. Let's even see if this connects to OpenGDB. Sure. OpenOCD, not OpenGDB. Maybe IPv6 wasn't such a great idea after all. Yeah. Config to get the IPv4 of this Raspberry Pi. Restart OpenOCD. And kill the tests. Set this value to IPv4. I just copied it. Okay, npm test. Oh yeah, I also needed to run the tests one by one, not run them concurrently as Jest would usually do. So it doesn't hit the GDB server with concurrent requests, which will obviously not work. And let's see what's going on now. So we are running those tests pretty quick now without these DNS issues. And we'll have the result in a moment, hopefully less errors than last time. Meanwhile, we can start writing the commit message, fix 40. Just copy the description for the issue. Yeah, so we are down to 6 failed tests and yeah, invalid single step response. So that's probably a test that shouldn't even, I'm not sure if it's valid this context. Yeah, then what do we have here? So this is the LDR thing, pop, we had it, we add it as well. So yeah, so we no longer see the issues with the SP registers, but we do have some other issues we'll look into shortly. But at least we know we fixed that, and those tests now pass both against the silicon and the actual Pi Pico. Issue number in, close in. Yeah, right. Two less issues to worry, two less failing tests to worry about. Close now. Push went well. Yeah. All right. Before we go into the next bug, I just want to quickly fix those LDRs, because I think I know what the problem is. So go to those tests, do LDR test, and so there is RS. No, the tests 24 spec LDR was why can't I find it now? Something strange. Oh, it's instruction spec. They moved. Okay, so in this case, I think the issue is that we are writing uint 8 and there is probably some garbage, so it would probably be best to, you know, write uint 32. And yes, here we are again, LDR, so let's write uint 32 just to make sure there is like no garbage. And there was another one which was, oh, this one, yeah, so maybe that's the same issue with the top. Yeah, let's, you know, writing there, yeah, let's write them all 32 bits, so so there isn't any garbage in the memory. I mean, when we run it in the emulator, then the system state is clean, but in the Pi Pico there might be some other stuff, so it's best to, you know, just write the entire integer. And now if we run those tests again, then we should have even less failures, less positives, negatives, I don't know. So instructions 6 fail on silicon, right? Yeah, first of all, we can see like the situation now is much better. We have only 3 failing tests on the silicon, and this one are probably false negatives. This one is interesting. There is like probably a bug here if we get a different result, and we'll look into that in a moment. But yeah, need to be first, then would be used memory content. Okay, so just fixing this test give us false positive because of an issue with the test itself. Okay, so we have this last instruction that doesn't return the same value on the silicon, this add R1 IP, and it says n should be true. Like on the silicon it's true, but let's take a look at the test. But in our test, in our like emulator, it's full, so it seems like a bug. And let's try that one. So RP2040, let's figure out why it's false and why it should be true. I mean, this RP is probably R12, so we are setting R12 to 44, and that's interesting. Don't think it should be negative, like it doesn't seem negative. Maybe this is, let's try to dump the register. So u dot usg tester dot b as this client, dump the value of all the registers when this, oh, we can just console.log registers here. Okay, let's now and it only tells just we only want to run this test case, so we don't have to wait for all the others. And interesting, we are adding R1 to R12, and yeah, it reads 110, 44. Why are all those flags true? That's interesting. Do we need to reset them before we begin test? I think we do. Not sure. What happens if we set X R zero? Now that should set all the flags. Still fails. Oh, now R1 is not equal. Change something. Oh, row 40, 10, yeah. 6, 44, and now these are all false, but didn't update the result. Interesting. Read because I only had this single test case. Like, let's see what happens if we read those registers twice. Well, oh, maybe setting XP star to 0 wasn't after all. Let's see if how do we deal with it in the test driver. There are probably other tests start on the flag, so we should reset the flags probably. Don't remember if we did. Yes, best way to do it is when we initialize it, we reset everything. Maybe we should also do the big client clear all the flags. I'm not sure if reset init does that. I mean, we can check probably. Multi-arc target remote Raspberry Pi 3 registers. Oh, let's monitor reset init for registers. Yeah, it seems like those flags are clear after monitor reset init, but we don't. Yeah, it happen after each test. Yes. Interesting. Let's try to read the registers also for the test without zeroing out XPSR and seeing what happens. 4 and test again. Yeah, now we can see that even before we had those flags set for some reason. Not sure why they are set here, even though yeah, I guess we just to clear them when we have this init, just to make sure that all the flags are clear. So we have we can register write registers dot registers and just set them all to overflow is B. Cool. I think that would probably fix this test case. Yeah, now it passes. So there was no bug. The only issue was with our testing framework not resetting the register. So again, let's just run everything one more time to see that actually fixed now. Yeah, I wonder why the case always likes to fail. Oh, maybe because we set XPSR here. Why did we set XPSR? I think also to zero out the flags, and I think setting XPSR may mess with the state or something like that. Try to remove it after we finish this. So now we only have this one that fails, and let's remove this XPSR and see if it helps. Then fine, probably. And then we only have this SV4. Sure. And be in. Yeah, I don't think I would worry too much about this one. We are doing, I mean, it's a very specific test case, and yeah, now only this one fails. For some reason it replies with OK to this single step. Probably has something to do with, I mean, what happens if we do accept OK as a response? Let's just, try to see if this helps in any way. Like a quick win. If we can fix it, perfect. If not, then it isn't the end of the world. So client parts. The response isn't okay as well. Yeah, so I think this is probably something goes wrong when we raise this exception. Not sure, but don't want to spend too much time debugging it, so be happy with what we have right now. So we probably fixed the other false positives. Don't want this. Why it's a good idea to review this or the changes before committing. This test initialize tags 0 silicone. Like previous commit. Yeah. 0 tags silicone. Number of false positives. Okay, cool. So yeah, so to summarize that, I think we spent like the last stream something like 4 hours just writing this whole framework so that we could run the tests against the silicone. And the good thing is, the good news is that we only found this issue with SP. The other things were just false positives, so we found one issue. And I think, if I'm not mistaken, of all this stuff, I think, if I'm not mistaken, we found a bunch of I have all those saved files. Anyway, we found a bunch of bugs while implementing the GDB client, and it's been a good experience and bumped our confidence. but overall I don't think it found any significant bugs, which is also a good sign. But in a few minutes we'll see how I evolve this tool that we built, this GDB client, into another tool that is actually super helpful in finding bugs. Before we do that, let's go back and look at two other bugs that I found. So this one is a very tricky bug. It took me like, I think, 5 or 6 hours just to find it. Just in short, how I even found it. So I had I don't remember. I tried running one of the demos from the I think one of the GPIO demos from the Pi Pico examples repo. I think that was let's see if I can spot it real quick. Pico examples. Yeah, so I think it was like the demo, this IRQ demo, trying to see how it works with IRQs, and then it would just do all of strange things, and you know, PC, the program got into strange addresses. So I started debugging it, and eventually I found out, like, I resorted to our most fundamental debugging way, which is just printing the address, the PC, for every instruction. We already did it a couple of times, and I found out that the last instruction that was executed before PC went crazy was always in the end of not just this function, but I think there is like some kind of IRQ handler in the SDK. Let me show you where I found it. Like, I think it's GPIO fallback probably. Oh yeah. So this function, when you look into it, we can open this in GDB so you can see what I'm talking about. So this Pico OSK, or maybe we can actually code cd Pico examples, cd fields, cd GPIO, the hello GPIO IRQ, and then there is this disassembly file that's quicker way than starting GDB. And if we take a look at this GPIO IRQ handler, we see that it ends with this pop, R4, R5, R6, and PC. And I noticed it always went crazy after executing this instruction. Now, this is an IRQ handler, so I started like instrumenting exception entry and exception exit, and show you. So we have this exception entry. So just printing the stack pointer whenever we got to exception entry, and then in exception return also printing the stack pointer, because I assume that since we have this pop which is return, like returning from the function, and this is the exception handler, it went right into exception return, and then it loaded the values of registers, and then it loaded the incorrect value into PC. And I just console logged, and I found that yeah, indeed it loaded 0 into PC. So I printed all the stack pointers in this prime PTR at the beginning of exception entry and exception return, and I found out that when we entered this exception, we had a different value than when we returned, and that's something that modified the stack, and the value was exactly 16 bytes, 10 hexa, so that accounts for those 4 registers. So this immediately made me look at pop or push as one of the possible culprits, and it wasn't too long until the issue became apparent to me. So if we take a look at this implementation of pop, so whenever we pop registers, we just have this address variable that we update. We add 4 for each register that we read, and then for the final register, we are just adding this 4, and then updating SP. And the thing is, usually this works because people pop stuff and it reads the registers and it updates the SP at the end with the address. But when we call bxWritePC here, the SP hasn't been updated yet, but we do have this call to exception return if this condition matches, and in exception return we are actually reading from SP. So the thing is, we have like incorrect order of things. We are we should update SP before we call bxWritePC, because it might read from SP and it expects the stack to be balanced. So it expects the SP to the pop to have been executed already. And the funny thing about this, that I don't know if it's funny or it's sad, but if we check out the pseudocode for pop, they don't mention that. This is like I think this is a bug in the datasheet. Yeah, if you check out the pseudocode for pop, you can see like it first of all does all these writes, updated, reading from memory into the registers and calling load write PC, and only at the end it updates SP, just like we did. But apparently, if we take a look at load write PC, it calls bxWritePC, and bxWritePC calls exception return, just like we do. And then in exception return, they call this pop stack, which is reading values from this stack. So I think, double check this, but I think, yeah, frame PTR is looking at SP main, so the stack pointer. So yeah, so I think this is a bug in the datasheet, and they should probably fix this. But this is why we probably haven't, when we implemented this function, we haven't thought about that specific edge case. Okay, so to fix it, first of all, let's write a reproduction test case. So 40. I think we have a test case for exception entry and exception return, but let's just make it a bit more interesting. So exception entry and exception return with push and pop. So in this case, it's going to be, I think, the most complex test case we have so far. We are going to do something like that. So we have like this exception handler, which has those 2 instructions in the original test, and we are going to change them. So in this case, we are going to just, we can take this this push. Do this, or maybe, or do we set up those instructions? Yeah, code. We have this for push, and how does this work? Just m boolean. What is m? Probably m means we are pushing LR. Don't remember. Let's check it out. Push. And probably, yeah, and probably we are pushing LR. So yeah, it's true, we are pushing LR, and then we are also pushing for R5 and R6. We can just write it as a bit mask, that would be easier. Those registers, and then the next opcode will just opcode pop, and we are popping P is PC probably, and then popping the same registers. Okay, so now we execute instruction. So this point don't want this, and let's also have like this just in the middle, another opcode that will just move a value into R0 like we have here. So for not to R0, to R4, so we can check the whole mechanism that it works. So we are going to move to this constant R4 equals 4. Yeah, so we are going to move some value 42 into R4, and then at this point we are going to execute one instruction and expect PC to go into this handler, and we expect and then we can execute another instruction. It should execute now this R4 42, and we expect R4 to equal 2, and then finally we just pop instruction, and this is another way to return from the function, just pop PC, and then turn to the original address. That's cool. And then let's start with R4 that equals to 105, and then we expect it to be restored. And let's see what else. Oh, +4, yeah. All right, so yeah, now we can see the bug. This is exactly the bug that I had, because obviously this sequence of instructions should just push a value, save the values of those registers, then update R4, and then restore those registers. And yeah, we can see R4 was updated here, it didn't fail. But then when we call this instruction, PC went crazy. So now we are going to fix this bug after we have this test case that reproduces this complex situation. And the fix is going to be pretty straightforward. So in this case, we are just going to instead of updating SP after the fact, we're just going to say this SP is just updated to address +4 before the fact. And yeah, so this one works. It returns to the original place, but then I wonder why R4 is now 0, why it hasn't been restored by the pop. Values that we read. This. Four, 5, 6. Yeah, interesting. It seems like pop is executed twice, but it's just this test. Still seems. Oh yeah. Oh, interesting. We push and pop different registers. Yes, we did. Yeah, there is a bug here. This should be one more 0. So yeah, so it pushes 0, 1, 2, 3, 4, 5, 6, 7. Yeah. So yeah, so now the test passes. The issue was with the test pushing the different registers and then popping the correct one. So obviously this is why it failed. And yeah, now we have another pretty tricky bug with exception handling that we fixed. And this would only affect functions that exception handlers that have this way of returning. exception handlers that have like bxlr, like this is probably what we have in most functions. Like, let's see how many of those we have here. We have here 36. Yeah, we have here 36 bxlrs, and I don't know how many pops with PC. It's harder to count. Yeah, okay, this is also pretty common pattern. So yeah, so now we should be good even with either way, returning with either bxlr or with pop. Cool. So one less bug to worry about, one more squashed bug. Move here though, something that we forgot to commit, or what? Oh, it's just a missed semicolon. I wonder why Prettier haven't coded that. I'll have to look into why Prettier isn't running when it was, should have been called by Prettier. All right, so yeah, so you can see that the fix is pretty trivial. It's just moving this assignment to SP one line up or a few lines up, but it really matters. So with that, let's commit this fix. Pop and play together. One. Yeah, it's fun. We killed 2 bugs in less than 1 hour. Less than 1 hour. Cool. Let's do the third one. This is actually another interesting one that was the bug. Yep. So this is actually another interesting one that says that in this datasheet it says that yeah, those like are the hardware interrupts that we have on the Pi Pico, but you can still force the other missing interrupts 26 to 31 that are supported by the Cortex M0 by writing to the NVSIC ISPR register, and we implemented that just to set an interrupt in software. And let me show you where I encountered that. So again, it was while I think debugging one of the Arduino cores quite wouldn't work in certain situations, and this was something that was ended up being timing dependent. There is this USB driver, and we haven't implemented USB, but it still runs. And there is like inside this USB driver, there is, I think it's, who calls this? It's one of the places where they call this stud. Yeah. It will take me a short while to find it. Place where I encountered this. Here. We have like this mechanism. Oh, I think, yeah, here. So in STD-IO USB, which is used by one of the, I think, the unofficial core for the Pi Pico, the unofficial, they initialize this STD-IO USB, and then they have this code that initializes it. And they have this timer that they set here. You see, they set they add alarm, and we haven't implemented alarms yet, so it shouldn't be called. But then inside, somewhere deep inside this add alarm, they have this like logic that they check the current time, and yeah, add alarm on the lock. Yeah, alarm. Target, I think. Oh yeah, So they have like this alarm set target, and eventually at some point deep inside they checked if we missed the time for the alarm. So if the alarm happens like 1 microseconds in the future, and 1 microsecond that is already passed by the time we got into this line, then we'll set a flag that said we missed the alarm. And usually that wouldn't happen. I mean, this timer that they are adding in this STDIO USB, it has an interval of 1 millisecond, 1000 microseconds. So 1 millisecond, it is a lot of time. But I had a case where I think on my phone, trying this on my phone, this would actually miss the alarm, and it would, in case it misses the alarm, I think we can see it somewhere here. Yeah, if the alarm was missed, it just calls the callback immediately. And long story short, this whole thing created the situation where in some environment, like on my phone, timer task was invoked immediately. And what timer task does is just set this IRQ to pending, and this IRQ is IRQ number 31. So setting an IRQ to pending, just writing to this ISPR register as they suggested in the datasheet the number of this interrupt, which is 31. So they fire this interrupt number 31, and this basically they have this handler set here to this same interrupt 31. So that's a strange way to say I don't know why they did it like that, and not just instead of just calling this code directly in the timer task. No idea why they did it. Maybe for some reason they need to run inside interrupt context, and this timer task doesn't necessarily run under interrupt context. Truly no idea why. But anyway, they fire this interrupt, and then this code runs and basically does nothing. But on my phone, it would get hung in there in this, just firing the interrupt again and again and again and again. And then I started digging, and I found out that there is an interesting behavior here. Yeah, this is the link to the place I just showed you. So the datasheet has this NVIC behavior somewhere, and it's pretty tricky to understand, but it says that the NVIC is going to update this pending, which says if we have a pending interrupt, if either we have like interrupt assertion or somebody wrote to this ISPR field, then it will set this thing to pending. Otherwise, it will clear it. So if we have like clear pend, and clear pend happens on exception in, and exception in returns true if exception entry is in progress to activate int num, or if interrupt the assertion, which means the hardware tells us to clear this interrupt. So what I understand from here is that whenever we enter an interrupt, we should probably implementation defined. But whenever we enter an exception entry, interrupt handler, we should probably clear this interrupt flag. Now, this, I'm not sure this is true for hardware interrupt on the Pi Pico, because I think it's up to the hardware to like, we take a look at, for instance, timer, we can see that it has its own bunch of registers that we can WC means write to clear. We can write to clear the interrupts, but at least for user exceptions, based on the fact that the code in the SDK doesn't clear this interrupt flag, and unless we will do it, it will just keep firing on repeatedly. Then I'm pretty sure that at least for user-defined interrupts, which are like all those greater than, I think, 26, right? Yeah, all of interrupt numbers greater than 25, then we have to clear that flag. That's up to us. And for the other ones, we'll have to see probably on a case-by-case basis. So let's write a test case and do that. So the test case is like this. So yeah. So the test case is basically saying something like should be turn. I think we messed up a bit. $20.40. Back and accept return. Yeah. Should probably another each case in the existing describe and not a different one. Turn correctly from exception with pop LR. So yeah, so now just makes a bit more sense that both these are under exception entry and exception return. And usually I don't do it, but or I try to avoid doing it, but we can just amend the last commit. If somebody else is working on the project at the same time, that could be disastrous, but I hope nobody is working as I'm live streaming. But if you do, you can let me know in the chat space. So we are going just to say the last commit, then force push. Yes, I know this is destructive, just last commit. So don't have this dirt in commit history. Now if we can git log, we can see updated the previous commit. Cool. So yeah, you have this test case. Oh, we need this new test case, so let's add another test case which says should clear user interrupt, clear pending interrupt flag, case IRQ 24.5, and in this case we are going to execute 31 just as in test cases. 31 handler have 31, it doesn't really matter here, just to make sure that int 1 and 31 in 31 1, and we don't care about this, don't really care. Let's open up here, we don't really care about, we are not now testing, just want to see that this flag is cleared, and then we expect pending interrupts to equal 0. That's the only thing we want to see, that it cleared this pending interrupt there. So for this, for executing the instruction, this should probably be think so. Yeah, we are. Yeah, we can probably do it by two and by the IPSR. Oh, and one shifted by 31. That explains this funny value. So cons NV IPSR is this value. ISPR pending. Okay, so we are setting this hierarchy 30 pending, and eventually expect P20 reading 2 and reading it back after the interrupt handle. So before we execute the instruction, we expect it to say that int32 is pending, and then after doing it, we expect it to be 0 because exception entry should clear this pending interrupt. So we clear the pending interrupt flag entry for user hierarchies. Okay, so NVIC IPSR should also equal 0. Cleared flag is cleared. Okay, so we have the test case, it's failing. Now let's just implement this. So in exception entry, we can say something like that. So if we where's that exception? Yeah, so maybe even here when we call exception, only happens for interrupt. Here in case of an interrupt. So if this is an interrupt, then we just if interrupt number is greater than 5, the max hardware IRQ. We'll define this 5. The maximum one is the RTC IRQ. Greater than this, then these interrupts. Move this pending interrupt. This. Just clear this flag, and now this is green. Perfect. So yeah, another behavior, and do is also by force hardware interrupt the issue, and then I'm not sure. We'll probably encounter this, but if you have some idea whether this should happen in case of hardware interrupts or in case of hardware interrupts, they keep being asserted until all of them keep being asserted until the hardware clears the interrupt flag, then let me know. Otherwise, we have this to do. We need to figure this out sometime in the future, but for now, at least for user IQs, we know we are clearing it, which is probably the correct behavior, and then we can fix 40. That's 2, fix 22, right? And another bug fix. Another bug fixed, yeah. So yeah, and we have only one left, and this one is quite interesting bug. I found it out yesterday when I was trying to create a code that just dumps the list of interrupt handlers, just reading from Vitor all the addresses, something I wanted to show in the course in the next session. And then I found out that when I print the indices of the interrupt handlers, then numbers between 11 and 15 aren't printed correctly with printf. So I managed to narrow it down to just, calling printf, and calling printf 12 is %d, and then passing 12 would print this. And I managed to so this is only happening, this doesn't happen with the Pi Pico SDK. It works correctly when you run this code inside the main function of the Pi Pico SDK, but it does happen with the Mbed Core. And let me show you this in action. So I already compiled this code into this this test printf.ino.hex, and if we just comment, so it runs. If we just npm start, then it fails. It miserably fails. Why does it fail? Oh, because it's already running. Yeah. So if we just npm start, you can see it fails. Like we'll probably print to it says 12 is less than, and I will just run the same code on the Pi Pico so you can see that it runs differently. And Pi up the serial interface on the Raspberry Pi. I connected it through a serial adapter to the USB port, so it's using the hardware UART on the Pi. And then let's multi-arc target remote Raspberry 333, and then we are going to Raspberry Pi, and then we are going to just load this file through GDB. So upload the code through GDB. Load. Can we do it with an X? Yeah. So now we uploaded the code, and side by side, so we can see the output on the real Pi. And then I'm going to just monitor reset to start the program, and you can see it says 12 is 12. So again, monitor reset. On the real Pi, it says, on the actual silicon, it says 12 is 12. But in our emulator, it says, where is that? Here, it says 12 is less than. So this is the bug. Very strange behavior. And my initial reaction was, okay, so maybe I could debug this function that and figure it out that way. So apparently, even though we built this Arduino code for embed with EmbedOS Arduino Core with debugging symbols, this function is a library function, is a C library function, so it's not part of EmbedOS. It's part of the C library, probably newlib, and it doesn't come with debugging symbols. It's part of the toolchain, and I thought maybe we could debug the assembly code, but then I took a look at the implementation of that function. This is the implementation. I don't know if this is the same version that I have, but you can see it's very, very long. So debugging this without source code, even with source code, that would probably take some time. But debugging this with assembly would be total horror. If anyone of I will post this link in the chat if any of you want to just get a better feeling of the horror. So yeah. So instead of doing that, I decided to try a new approach and built on this GDB client that we created last week. So I think this is where it really becomes useful, because I created a new tool, and we are going to use that tool right now to debug this issue. I already did it before, so I know what the issue is. I still haven't fixed it, but I know where the issue is. I just added a comment before starting explaining the issue, but let me show you how I found it and the new tool, because I think that's super cool, and that's gonna help us find all of those subtle bugs that hide somewhere in the simulator. So this new tool is pretty short. It's called gdbdiff, and what it does, it takes the same piece of code and runs it instruction by instruction, both in the emulator and on the silicon. And while it's doing it, it's also checking for differences in the registers. So it basically just traces the code line by line and seeing where the first place where we have different behavior happens. And it's actually pretty short, less than 15 lines of code, and most of them are, or some of them are comments and debug prints. And what it does, it just creates 2 GDB clients. One connects to localhost, to the emulator, run to the Raspberry Pi. Then we disable interrupts by writing 19 as I think the Primark register, right? Primask is the Primask register, if I'm not mistaken. We can see it probably in this GDB test driver. Yeah, Primask. So we are writing one to Primask to just mask interrupts, disable them, because if we have some cystic interrupt or something like that, and we obviously can't, unless we have truly cycle accurate emulation, we can't make sure that the interrupts will fire exactly at the same spot. So they will, so this way we just make sure the interrupts don't interfere with our testing, with our comparison. And then we just read the registers from each of those GDB clients, so from the silicon and the emulator. And if we find any difference, we just say print out the differences. So compare registers will print out, will compare the registers one by one and print out all the mismatches. And then we also print the PC, so we'll know where this happened. And if otherwise, if the registers are equal, then we just step one instruction in both the emulator and the Pi and the silicon. So yeah, that's I think is going to be a real game changer for us. And let's run it and see it in action. So the first thing we want to do, we want to make sure both the silicon and the emulator are running the same code, and we already loaded the same hex file into the Pi Pico. So the next thing we need to do is just to make sure they are both in the same point. We don't want to run everything from the beginning, because then we have a bunch of code that is running that we are not really interested in debugging right now. We just want to get to this line inside this setup function and run it and see where the first difference in execution occurs. So let's do it. That's file. How did we call it? Test printf, right? Test printf. printf.eno.health. So we have the debugging symbols. So now we are going to connect. We are connecting to the Pi Pico. Yes, load the symbol files, and I'm going to reset it. Monitor reset init, breakpoint in setup, and continue. So now the Pi is just before this call to printf, and I'm now going to do the same in the simulator. So connect to the emulator and just stop it a moment before calling the printf, so both are in the same place. So I disconnected from the Pi. Let's restart the emulator, and this time we are not going to MCU execute, so GDB gets control from the beginning. So restarted the emulator, connecting GDB to the emulator at WinHost. Yes. And same, breaking and setup, continue. And this takes a bit longer because we are a bit slower. And also now we have both the GDB, both the emulator and the simulator and the silicon stopped in the same location at the beginning of this setup, just before calling printf. And now we are going to run the new tool, and it's going to produce a lot of output, because this tool that we have just seen, this gdbdiff, is printing, it's dumping the registers after every single instruction it executes. And the reason for that, as soon as there is like a disparity, we want to see what happened just before. So the values of the registers before the instruction that that caused this disparity. So let's run this. npx dsnode debug gdbdiff to gdbdiff.txt, whatever, and now it's running. It doesn't really, we don't see the output, but you can see it sent the output to this file, running all those instructions and dumping the registers, and it continues until it finds a difference between the silicon and the emulator. So if we go down, all the way down, we'll probably find a difference. Apparently there is no difference. Maybe we need to look at it, reload it. Yeah, all right, yes, yeah. We can see there is a difference. There is, we found an instruction that behaves differently on the emulator, on the behaves differently on the emulator versus the silicon, and we found 249 instructions that behave the same, which is very good news. But yeah, I think this is a much better way to get a good confidence that we are running very close to the real silicon, because unlike those tests, which are great, but we have like 100 of them, here we already tested more than 200 cases. So it's much faster to validate our implementation this way. And then the nice thing is, since this tool stops as soon as it detects this issue, we can just now go with GDB and connect. It doesn't really matter to the Pi Pico or the emulator, and then it will be stopped. You see, it's the same address here. It will be stopped in the problematic location. So if we call this assembly, we can see this is the function, and then we can see this is the next instruction. So this was the instruction that caused the trouble. So we had this instruction, and let's just run this side by side. So write down the details. So this is the instruction, and we can look at the register dump just from before running this instruction, and we can see that R3 had this value of 0, and R12 had this value of this value. And the problem was, you can see there is a mismatch in register 16. 16 is XPSR. So if we check it here in for registers, we can see that here this is the this is silicon. This is like this value. But if we now switch DB and connect to the emulator, so WinHost, yes, in for registers, we can see that there is a different value for XPSR. So emulator. So, and that was the only difference. So Ed indeed added those numbers, but for some reason in our emulator there was like make sure they are like the same number of digits. So we in our emulator there were like 2 flags that were enabled and not in the silicon. So to understand that, let's first of all see what are those flags are. So RP2040 R. So yeah, so these are like C and Z. C and Z flags. And I can already see why this is a bug, because adding those numbers, adding 0 to this number doesn't have any, the result is obviously not 0, and there isn't any carry. So yeah, this seems like a bug. Let's check out, no, first of all, let's create a failing test case for this, and then we'll fix this. So yeah, where is that? In instructions now, add, and this is adding to registers. Have even a test case? Yeah, adds. So is it adds or instruction? Is that exactly? Well, so this is add R3 R12. So one is this one, add reg. Sounds good. So to add R1 IP, R12 is IP. That correctly. So this is the already have like one with setting this. So yeah. Correctly, we are adding R3. In this case, R3 is just 0 and R12 is value, and then expected yeah, so in this case we expect R3 to, I guess, and check value in the output file. No, we don't see it here, but we can just info registers to see the output. But yeah, R12 shouldn't be changed. What does, then we try the result to R3? But anyway, we expect that will is R12, yeah. We'll just call it R12, so more in line with the name of the register here. Let's 12. Okay, then yeah, we accept all of those defaults. This is what the silicon does, but for some reason we get true. Now we have this failing test case. Let's see what. Focus on this test. Variation of add register. Yeah. Ooh, wait, this going on here. Yeah. So the destination isn't SP and it's PC. So we are this is the result. Let's see what the result here. Result 16. Yeah, the result looks legit, and obviously the result is 0, so it is negative though. Is it? Yeah, it's negative. So why isn't here we had different case though. We had carry and Z set in the emulator, right? 6 is 2 and 4. Where is the are so 0 and carry didn't have negative set. This is also strange. I do expect the result to be negative, but either the chip, the silicon, or the emulator set it. Wonder, maybe we had carry set before, and that's the reason why we didn't get a negative result. How should carry affect that too? Let's take a look. Flag status just before executing the instruction. Here to add. One more thing, I want to verify that it's the same opcode. So we are testing the same opcode as we have in this binary. So opcode should be 4463. Then if we check out this assembly /r, so we can see the opcode 4463. Yeah, so it's the same opcode, and then we're looking at the correct instruction, or are we? Yeah, I think it's actually the next that has this issue, not the yeah, probably the next, not the add. Maybe we are looking at the wrong thing, because no. Yeah, so this is the PC where we had a mismatch, but the PC is after the instruction is executed, so it seems like the add was the last thing that executed. But I think what we are seeing here is like the registers after executing this thing. It first dumps the registers, then it so this is the state after executing the instructions. Go one back and the value is there. So this was the value of R3. So now it makes a bit more sense to me. I think this was R3, and then this was, yeah, and the result is 0 indeed. So I wonder why the flags are different. So first of all, let's update this here. Back. And failing instructions. Yeah, so in this case, we are adding this value to this value, and the result, we can see it here, like 0. Here, probably if we do info registers, the result is 0. So why isn't this 0 in the carry? Why shouldn't they be set? It seems like they should be set in this case. Oh, yeah, R3, the result. That makes sense. But yeah, now we get the same behavior as we see, like this is true and this one is true, which makes sense to me, but for some reason it doesn't work like that on the silicon. So let's try to figure out why. So we have this add instruction, this one, and the result is, yeah, it's like big number, larger than uint32. And let's take a look at add register. Maybe it doesn't update the flags, and that's the thing we are missing here. That add register. RMRDN, RMRDN, probably this coding. What is DN? Oh, nation. Could be like, no, it could be like any of the registers. There is a destination. If set flex and set flex is true, yeah, set flex is false for this encoding. So yeah, this is a bug. We shouldn't update the flex in this case. Set flex is true, is false. So yeah, we found a bug. We don't need to update the flex. Let's just do that. The correct encoding. Oh, sure, Tomasz. Thank you. Good to see you here. And yeah, I think we are pretty close to squashing all those bugs, and then we'll go with the MicroPython. Anyway, 0 1 0 0 0 1 0 0. Yeah, that's the right one. So yeah, we just don't need to set a flex here. Don't, right? Set flex is false. So no need to set a flex. And yeah, less code, more fun, more joy. And now this is probably, so maybe we should say shouldn't not update flex following add the instance. That's D2. Yeah. And all right, so we fixed another bug. We found another bug that I wasn't aware of thanks to this new tool, and fix it. So let's meet that. And on this log here, of course. Yeah, so I wasn't aware of this bug. For some reason it didn't pop up in my previous testing. Probably something different in the way I wrote the test code or something like that. The test program before I narrowed it was a bit different. It had a for loop before I narrowed it down, so maybe something changed there. I don't know why. In this case we found it, but I'm happy we did, because I didn't find this this issue before. Fix API for the update. Right. Update flex in it. Okay, cool. Bug found in application. Cool. So now that we found this bug, let's see if it somehow I guess it didn't, because I know in my testing I found a different one which I was hoping to find, and maybe we'll find in a moment. But before we do that, let's just run the emulator one more time, this time with the bug fixed, and see if we get any different behavior now. No, 12 is still less than. So let's continue running gdbdiff, and I hope this time we'll find the bug that I found earlier that caused that. So where are we right now? We are WinHost. That's the emulator. So breakpoint at setup, continue, and it should stop at setup just before the line that misbehaves. Go back to the Pi and monitor reset init to restart it. Breakpoint at setup, continue. And I think this is probably something we can also add to gdbdiff, like send this monitor command, reset the Pi and reset the emulator and set a breakpoint, etc. But that would be probably a lot of work to figure out the memory address and stuff. So I think this is sort of a sweet spot where we sort of do this very small initialization with GDB, and we can probably write like the entire command line to do it in one click. And then once both the simulator, the emulator, and the silicon are in the same state, we just run gdbdiff. So let's run it again, this time after fixing the first bug. Let's take a look at the output. So we expect at least 249 instructions to run without a problem. And then, yeah, now we found another mismatch. Interesting. Just a few instructions later in instruction number this, and again it's this flex. Yeah, this flex is causing us a lot of trouble. So see, there is one here, and what does the emulator have? Yeah, this is like the emulator, it has one. So I think one is the 0 flag. Let's see, IPR. Yeah, no, one is the overflow flag. Okay, let's take a look at what GDB says about this. Yes, assembly. Where are we? We are just after ADCS. So this happens in some ADCS instruction. Instruction spec. So this is ADCS R3, R2. So let's create a test case for that and then find the bug and fix it. Do we have ADCS? Yeah, 5R4. Let's create another one. Do we have like this test case repeating twice? Yeah, no, we shouldn't have the same name for those. So there is probably, yeah, this one is that negative and X. Yeah, this one's this action date name on the same test name. Cool. So what else? Yeah, it says we said we had ADCS R2, R3, R3, R2. So let's create this, convert this in test case. So duplicate this one, but this time 3, 2 was R3 and R2. R3, R2, R3 with R2, and set the registers to the values that they had in this. So this is the after values, and this is the before values. And we need to take note that we also had some of the flags set here just before. And we need R2, which is 0, and R3 is also 0, right? And after R2 is 0 and R3 is 1. So R2 is 0, R3 is 1, and what flex do we have here? 4, it's 6. So I think 6 is carry and 0. Are carry and 0. So carry true and 0 is true. Carry and 0, that's 6. So that's the before state. And then the after state, we expect R3, right, to value of 1. Then, ooh, why does it do? As here 1, this is like the Raspberry Pi, so F1. Yeah, oh, yeah, I know why. Because 0, it starts with 0, not with 1. don't need this comment, it's not relevant here. So those, so yeah, now it's good. And now the expected result should be in the silicon. None of the flags are set like this. See it here. SPSR is like the highest nibble. The flags are all false, so it should all be false, but it's not, because we have this overflow register that it's set in our emulator. So we need to find out why. This is ADCS, and we have this overflow. Oh, bad. Yeah, first of all, the result is 1, right? So console.log result, just make sure it's 1. Okay, so I guess the issue is if one of those greater or equal signs, they should probably be, one of them shouldn't be equal. So, but I'm not sure which one. So let's see. If both are, there is, yeah, I think I know the problem. I mean, if both left value and right value are 0, yeah, both is negative. This is not true. Like, I mean, this is true, this is positive, greater than 0, and this is greater than 0, but the result isn't less than 0. Yeah, but then this is true. I mean, left value is less than 0 and less than 0, and the result is greater than 0. And I think the issue is this condition is probably true, but we probably have to take into account that we add the carry. So we could either add this carry into one of those values instead of like just adding it to the result, or we can add it here, like checking also carry is less than is 0. I think this is a better way to go about it, not sure. Yeah, but it's, oh, now this one fails, and this one passed on the actual silicon, so I wonder why it fails. Carry is true, so there is obviously an overflow. Hey Puneeth, good to see you. There is obviously an overflow here because we add 1 to this, so we have an overflow. Then yeah, yes, not the best. Maybe we good to have those test cases to find those edge cases. So in this case, probably say this is 0 and this is 0. Yeah, probably if we are adding to negative value, then the result shouldn't be probably if we are adding 0 and 0, then the result should either be, so if we are adding negative and 0 and positive, then shouldn't have an overflow because go up, so fine. Like if we have -1 and we add 1, then result will be 0, so low. Yeah, I think this is probably, I'm not 100% sure about this, but this seems to be like a good way to fix it. Like the result is, if both the left value and the right value are less than 0, then and the result is greater than 0, then we had an overflow. That sounds good. I hope so. Yeah, with that, I think we fix another disparity between the silicon and the emulator. That's not overflow. With so when s heading 0 0 it carry. That shouldn't overflow. That doesn't mean we go from negative. We went from negative to positive because of overflow. Set overflow. Not set the overflow flag when executing 3 2 adding 0 to 0. Okay, I think that's good enough. All right. Copy 40. ADCS adding 0 0 0 plus 0 with carry shouldn't overflow. That over. Yeah. All right. So one more bug fix that another bug I wasn't aware I'm and let's restart this gdbdiffing thing and see if we can find any other interesting such bugs. I'm really finding it hilarious to have this. I don't know if hilarious is the problem. It feels so great to have this tool that can just find all these bugs, like this sort of magic wild card that just quickly finds any bugs that we have. Yeah, so a break setup, continue. So now emulator should be waiting at setup, and do the same in the Raspberry Pi. Monitor init, break setup, continue, and this is also stopped. Now we can start gdbdiff again and see if we get anywhere past 250 something where we stopped last time. So we are already at 273. That's not too bad. And did we find? Yeah, we found another issue with the this flags thing is starring here. But this time we executed 434 instructions, so we went even further. So yeah, let's see here. Where are we? Assemble. Yeah, interesting. Whew. That's interesting. We have like this. Why are we in handle error? Yes, shouldn't happen. Interesting. I don't know how we got into handle error. Doesn't sound fun. Not allowed in ISR context. Interesting. How did we get into ISR context? Oh, yeah, I think I know what happens here. Probably does. Wow. Yeah, so I think I know why we got into this weird situation. I'm not sure. yeah, I think I also know how to fix this. And I think I also know why we were getting different results in the in my debugging session where I found a different issue, which we still haven't stumbled upon yet, but it doesn't matter because we found other issues in this case. So in my case, I was debugging the second or the third call to printf because I had multiple ones, and I guess in the first time you call it, it mallocs something. And there is this thing in EmbedOS, I guess, where you can't call malloc in ISR context. There is like it's trying to malloc something like that, and then it requires some lock, and then this errors. Why does it think we are in ISR context? The reason for that is our code disabled interrupts in by setting up this primask gdbdiff primask. So, yeah, that's one problem with here when we disable the interrupt. So that's one problem with disabling interrupts. It may break some of the code. I guess here it just checks if primask is true, then it assumes we are inside the ISR context. That's my guess how we got here. So let's take a look at this error and then try to figure out how we make it not go into this interrupt issue. So, but the good news is that we run more than 400 instructions without a single disparity. And again, we have like we had like this TMP where R0 with 0, and then we have different result for sounds pretty fundamental thing for this works, pairing R0 with 0. Let's see what was the situation before and after the comparison. So we can see we had this value in R0. That's after the comparison. But before the comparison, I guess it shouldn't be changed. Value of R0. And then R has this flag set, which is 2, 0. $40. No, it's carry. We had a carry flag. Maybe that's one of the reasons we had this strange thing, strange disparity. Okay, so before this we had carry before, and then after this we have like Pi registers. We have A R A, which means what is A is like overflow and sorry, right. We have overflow here. Sure, overflow is causing us so much trouble at the moment. And what did we have in this? And we didn't have 0. Yeah, and then let's see what we have. That's the emulator. Registers 8. Emulator or are starting with 8, which is just this n flag. Oh, sorry, it's not. Okay, that makes more sense. So interesting. So I think the difference is that the emulator didn't clear the carry flag, and we did. The silicon didn't clear the carry flag, and we did clear the carry flag. Now it makes more sense when I decoded it correctly and I said it's n and not v. N. Wait a second. Negative either. Oh, it is negative. Yeah. Okay. Where did the carry came from? Or did we have any bug here? Let's see. So first of all, let's create, as usual, it's test case, instructions, cmd, yes, b, number, not here, carry, computing, R0, R, carry, set. So the situation is we have this 0, R0, and we have this carry is true, and then after that we expect negative to be true and also carry to be true, which is not the case right now, but it is the case later. Then let's go and see what happens. Immediate, let's do that. And yeah, we can see that we update all those flags, and let's see what the datasheet says. Maybe that's bug. Immediate carry. What is carry? Is adding the values carry. Not M32 and 1. And what are we doing here? We are just we don't think this should really, yeah, I don't think this should really matter. Maybe the problem is to actually, yeah, value is greater or equal, or greater or equal, less than, right? Negative. So let's see what add with carry does. We are adding rn, not IMM. I think we just have a problem with it's carry in, and carry in is always 1. Signed sum, unsigned sum, carry out. Okay, so carry out is if unsigned int result, unsigned sum. This Windows values your so unsigned sum. First x value find plus IMM8, which is 0, so signed, but we want the bitwise not of this, then we want signed plus carry is 1, so 1. Then we have the result, taking the converting it in this value into 30-bit values. Result, yeah, I think there was, in this case there should be carry. Oh no. Also 32 unsigned, so for them. Yeah, yeah, they do seem false. Yes, carry should be false. Range true on the silicon. Yeah, let's try to just see if this specific test passes when we run it on the silicon. Probably have run this test against the silicon. Interesting. So silicon says, did this runs? Not sure if this ran against the, and force it to run against Pi Pico. There is an easy way to run against the Pi Pico. Just start OpenOCD and see connecting. You can just say set this environment variable sure, and we can just Raspberry Pi. We don't care if it's slow, it's just test, and it connects now. Yeah, it connected, and yeah, is false. So I'm not sure what happened here. Why do we have this different behavior here? Like, are comparing this value to 0? Click on. Carry set. In our case, not set, right? Carry is number 2. Carry is number 2. Happen. For executing it, our test again. We are testing. R0 value and 0, and go with add a carry set. Now in our test we set carry before, right? Test. Yeah, we also set carry to true. It seems to be the same setup. Range, so negative, but why does it say carry is true even though it also passes? Now also pass on the silicon. Oh, that's funny. Now it failed. Oh, try that again. Oh, it should pass. Yeah, now it passes. Okay, that's strange. Just do another check. Is this a bug in the silicon? Okay. Now it is done. What happens if we start with carry that is false? Going to be true? Yeah, so it doesn't really matter. Initial value of carry here. Just adding, comparing this to 0 produces carries. Yes, maybe the thing is wrong here, but plus minus 1 plus 1 probably, the unsigned sum should probably be greater than doesn't individual components of sum. Oh, heard it with 60. That's the wrong opcodant. I mean, the test is doing one thing, but it says it's doing one thing, but it does a totally different thing. That explains some things, like why worked in a flaky way on the silicons and read a register we haven't up to test probably. Anyways, so now we can see that the unsigned sum does not equal result. Should have had carry. So yeah, so I guess so the carry calculation isn't should correctly carry thing. Doesn't matter if it's set or not, it should just set it correctly, and then the logic here isn't correct. So I guess when it says that this case carry in and result y, that is carry out that talks about the overflow. Unsigned row. So greater or equal than y, which code here, but maybe it looks at it x as unsigned int. Like it doesn't say here, but I guess it means to say x as unsigned was. Now it's green. So I'm not sure this is actually the correct interpretation of the datasheet, if x should be unsigned here. And yeah, and of this thing here, CMP register. I'm not sure if it's correct, but at least like this passes the test, so it matches. I mean, there are two ways you could interpret that, like if it's signed or unsigned. This is obviously, I think, obviously, yeah, it's always signed as far as I can tell. Yeah, always unsigned in our case. So yeah, the other way to interpret it, looking at the signed value wasn't working, so I guess this one works, so I guess this is better. And we have a new test case for that, so it's another small fix that we found. Where to commit that? No, only we want to execute all the tests. And what? Before doing it, let's run it one more time against the silicon. It should pass. Yeah, okay, great. I hope we did run it against silicon. All right, and before committing, I just want to run this differ once more time and see if it gets past 433. Make sure. So let's restart our thingies and run the differ again. So let's write also those commands. So that monitor reset init, break at setup. It should just now do everything automatically for us. Yeah, cool. And then for this local break setup exec. Cool. So now we are ready to run this differ again. Let's run it again and see if we get past 40 something. And we commit. We can happily commit. There yet? So it's not the fastest way to. Yeah, we got way further. So yeah, so we fixed that issue as well. Fix 40 very good. Get very flag incorrectly. Cool. And how are we doing here? Ooh, another one, another disparity again with these flags. Yeah, those flags are great troublemakers. Okay, let's take a look at this. So dash and emulator. Let's just connect to it. Don't execute without executing those extra things. Yeah, we went into printf and now we go again into printf just because we are inside the error printf, inside printf. I guess this is a strange situation, and all because we disabled the interrupt. So we'll try to work around this in a moment, but first of all, let's see. We have another bug here. The purpose is to find bugs, so it doesn't really matter which ones we find. Phew, that's the printf implementation, as long as but I think we just found the offending instruction. Yeah, that was CMP. Oh, again CMP. I don't like this CMP. So what's now? Open this file and see. So this is the instruction. Oh, I guess this is the same bug, but this time with registers. So I guess we have the same bug with CMP register, and we just found it. So Raspberry Pi and info registers. So here we have XPSR10. So it's the same thing. Carry, and this is like from the emulator without carry. And let's see the values of those registers. Well, R11 0, so -1, and R3 is 8. Yeah, so that's good. That should be like a quick fix, because we already know what the like we have already seen this in the other variation of P. Okay, CMP IMM, and then we have CMP very correctly, like we have correctly flag. Should correctly tank flags when it 11 and 3. Again, we are comparing R11 3. We don't have R11 yet, so let's add it. R11 just is just this. R11 this, right? And now we expect it to be both. Shouldn't be 0, that's sure. Yeah. Anyway, it should be negative, and it should carry without being 0. And now I have to figure out why things 0, because they are obviously not equal. Go to ARC2040. Focus on this test for a moment. Should register log value, write value, and see their values 8 and 8. Comes and maybe we have a bug. I think we have a bug in the encoding of this, or we are not using the right encoding. It two encodings probably. For immediate, no. For register, yeah, that's T2. The I registers T2. Yeah, okay, cool. So now the values probably make sense. They're using the correct encoding, and yeah, expected true, received false, and I guess let's see, console result. Yeah. Result is -9. -1, -8, or 8 minus -1 isn't -9. Something is strange. Left value and right value. So yeah, -1. Oh, that's probably -1 -8. Yeah, right. -1 -8 is -9. And borrow probably. Borrow. And in this case, say that left value is than 0, right value is greater than 0. Result is not. Oh, that's the overflow. So we didn't have an overflow, but left value isn't greater or equal than right value. So I guess it's the same thing here. Probably just compare those to unsigned, and it'll be fine. Or maybe converting them to unsigned, we should just keep them unsigned then here we can probably compare them to find calculate. Right. Green. Expected true, received false. How comes? Like what we had before. And change the logic. Is negative. Oh yeah, now okay. But yeah, let's give them. And actually say if less than. Otherwise, why do we even? Oh, we. Okay, cool. Yeah, so now I guess this is good. Let's just verify that this test case also works the same on silicon, just to make sure. Restart OpenOCD. So let's run those tests and see that it connects to the OpenOCD. Okay, so one more bug squashed. We should probably have some kind of victory sound whenever we squash this. Another bug. So start to it with thing. Yeah. Test case. Fix. Here. There. Then we can say coding 2 didn't set carry flag correct. Okay, so one, maybe we can amend and say found user. So we have some background how we found this bug, or why it even matters. All right, so well, yeah, another fixed bug. And now let's finally fix that issue with printf. So the way I'm going to do it is just I'm going to recompile the code to call printf twice, and I think in that way it will just printf just fix that issue with malloc, because it won't call malloc probably the second time. So we're just going to do it twice to make our life a bit easier. No, we can just breakpoint here. So let's recompile it. History grabbed Arduino CLI grab printf. All right, so one line to compile it. Compiling it, the Arduino CP test printf build ever to our project directory. Right, good, are good. OSD. Just execute it back, and now we have a new test printf that should probably not fall for this malloc issue. We'll see if now it finally reproduces the original bug that I found that causes it not to print the number correctly. So restarting our emulator, and then do bash and do this thing with gdb. And now the only thing we're going to change is just, instead of breaking in setup in the first line, we want to break in the second line. Maybe we can break in the beginning. No, let's just do it test printf. I think that was fine. 1, 2, 3 in line 3. Maybe it will work, maybe not. Let's see. That's against the emulator. Yes. Let's see if it breaks in the right place. Line 3. Yeah, it breaks in the right place. Cool. So let's do the same thing with the Pi Pico now. Set up second call to printf. Continue. Yes. And let's take a look at the output. Yeah, it printed 12 is 12, and I guess here we also see the output of the first printf, which is 12 is less than. And now we can probably, oh wait a range. I don't know what happens, but we should be inside the breakpoint. So let's restart that. That's Raspberry Pi. Okay. Yeah, interesting. Raspberry Pi isn't breaking the second line of let's try it differently. Let's try to break inside setup and then just move one line ahead. Don't know why it doesn't work. Strange. But anyway, just next here, and that didn't work. Are still not. Something is strange. The Pi Pico doesn't want to. So let's try something else. Let's try to break it. Printf. Then run this twice. Continue. Where are we? That's funny. Yeah. For some reason, yeah, it didn't work. Want to quit screen. Just restart it so we have an empty output, and then we can see what's going on. Want to reset init, break printf. Yes. Printing. Okay. Let's try going back to the previous approach, breaking line. Yeah, probably something is wrong with the breakpoint. Doesn't really break the correct line. All right. So back in serial USB.begin by the main. I'm thinking maybe instead of doing this setup, which does this main, which God knows where it gets stuck, we'll just do something else and code test printf. We'll just test printf to override main, so we don't have all this USB nonsense. Main. Now recompile it and copy it. Oh, now I know why it failed. Anyway, we already got the new test. Try to go with that. And the reason it failed is because we haven't uploaded the new code to the Pi Pico. So it was running the old code with the new debugging symbols, and shit hits the fan. So let's restart the emulator with the updated code. And then, hey Steve, bugs. Nice. I like this emoji for the backswash. Okay, so we have this connecting to the emulator, and then line 3 that we wanted to break. Cool. Yeah, breaking the emulator line 3 after we printed one 12 is less than. Okay, cool. And then let's same with the Pi Pico, but now we are also, first of all, let's connect to the Pi Pico without all. Yeah. Now let's also load the hex file into the Pico, load test printf.ino.hex, so it will run the updated code. We forgot to do it last time, that's why it didn't really work. And now we can set up this breakpoint in Pi Pico as well. Yes. Okay, now it hit a breakpoint, and yeah, we see it printed. I guess it printed once, and this one is from the previous run, and it also breaks same place. Now let's run the differ again and see if we can finally find that bug that I found after we found tons of unrelated bugs. So reminding you, this is bug with the printf, and yeah, what's up with the differ? Oh, have like interesting. So we have like some register is different. Probably this is like something that happens. I mean, it's at the beginning, so probably some kind of register, specifically 0 in the emulator is R0 is 8, and here it's 9. So let's just see what's the. So it's even before we ran any instruction, we started with sort of dirty state. So connect to the Pi and see what's going on here. Info registers. So yeah, like the values of registers. Compare them with dump. So yeah, I think only, it seems like only R0 it is different for some reason, right? As correct. PC should be the same. LR, yeah, correct. Seems correct, and those we don't care about them. So let's just, you know, set R0, just make sure. I'm not sure why it's different in main for some reason, but let's set it to 9. Oh, set it to 8. So gdbdiff has the same starting condition on both the silicon and the emulator, and run it again. Hopefully this time we'll catch an nasty bug. Yeah, it's running 36 instructions already. Still running 246 signs of bugs, yes, but it should. Oh, yeah, it found this bug. So in this case, you see we have like two different registers and 2 GDB. Then yeah, it doesn't really matter. They should both be in this place. Assembly, we can see that yeah, we can see that this is the offending instruction, LSRS, and we can also see that there is a mismatch, like side by side. So here, so we called the LSRS with those two values, and it produced a different result. In the emulator we got 10, in the silicon we got 0, and also the flags are different. And if we go one back, we can see like those values. So we see that R2 was 10 and R3 was 20 hexa, which is 32. So shifting by 32 bits in the silicon, it returns 0, so it clears the result. And in the emulator, it returns 10, which is A, which is it doesn't change the input. And luckily, save time, I have this test case, because as I told you, I already found it when this is the first thing I found when I developed this gdbdiff. The reason we haven't found it until now is because we had that malloc in printf. In my test code, before I narrowed it down, I had like multiple printf, and I didn't stop on the first printf, but in our case we stopped on the first printf, which caused malloc, which made us go a totally different route into the error handler and find a bunch of other small bugs in the implementation, mostly of the registers. This is the bug that I found. So we have the test case. We don't need to write it because I already did. That's in LSRS. So just paste it here. And yeah, it's failing. And now if we go into the instruction spec file, RP2040 LSRS, we can see that in the implementation, we can see that in the implementation we are just taking the input and shifting it by shift amount. The thing is, in JavaScript, in this case we know that shift amount R3 is 32. So in JavaScript, if you take a number and shift it by 32, for example, you get the same number. It's just like shifting by 0. That's how JavaScript implements that. And if we check out the datasheet, so LSRS, yeah. If we check out the datasheet, then see that we have carry. Yeah, inside shift carry there is like LSR and then yeah, and then it calls for LSR. It calls this SR type LSR, and then LSR just does first of all, it asserts that shift greater than 0, so it's probably illegal to shift by 0. Then it just 0 extends this input with extra shift bits. So if we shifted by 32, it would be extended to 64 bits. And then the result is just like taking those this extended number and looking at the 32 most significant bits. This does, I guess. And we take also next bit as like after the shifted bit, after the 32 most significant bits of this extended X, the next one is just the carry out, and then we return it. And in our code, we can say that basically if we are shifting by 32 or more, because it can be like any amount, shift amount up to 255. So if this is like 32 or more, shift amount is greater or equal to 34. And if it's less than 32, then we use the standard JavaScript shift. Otherwise, the result is 0. And now this is green. And I think we can also fix the carry. I mean, it works. In this case, it works well, but shift amount is 32, then it takes the bit 31. But then if shift amount is even more than 32, then carry should just false, because we'll look into those 0 extended regions of extended X, which are obviously 0, so 0. So yeah, so that's another bug fix. And before we commit, let's just make sure that this fixed the issue. Run, comment this mcu.execute, so start, and yeah, you can see 12 is 12. It worked. So this was the bug fix. This was the bug that caused printf to nonsense numbers. And the good thing, we didn't have to go through horrifying and long debugging session like we did or at least I did in the past to find it. Just running gdbdiff found a bug in no time. So I love this new gdbdiff tool. Well, buggy. Yes. 2 issue number 4, right? Fixes it. We have just seen it in our eyes that now 12 is 12. Right. Plugin S. Something or okay. File and good. All right, so one more bug found, and I promised we'll look into MicroPython. I mean, we could probably go and run this diffing tool for hours, and if you feel like doing it at home, trying to run this gdbdiff and finding even more bugs, I mean, you can probably do it with a bunch of programs as long as you don't need interrupts. Then like you set a breakpoint both in the emulator and on the silicon, just like we did here. You make sure they are starting from the same state. I mean, it would be interesting, for instance, to find out why when we got into main, our 0 was 9 on the Pico and 8 in the emulator. That would be interesting to find, if we can find the cause for that. So yeah, you just make sure they are both starting from the same state and have the same code loaded. Then you start gdbdiff, and voila, you get like it just spits the bug in you at you. And one interesting thing to improve here is just instead of printing XPSR as a value, just print the individual flag, so it will be easier to compare those experiences instead of having those strange values. And it can also like print instead of just those mismatches, like print test assertions, expect R2 to equal and the value on the silicon. So that's another cool thing we can improve here, but it's super useful. I love it. Anyway, before we sign off, I promised, so let's try to get MicroPython to run. I mean, we implemented a lot and we solved a bunch of bugs, so we may be able to. I compiled MicroPython, but instead of like the standard build, there is like a flag here. I found it in this SDK, where you can set this flag, and then it uses hardware UART instead of UART over USB UART. So we can interact with it without implementing USB. So let's just change this code to run micropython.hex and see if that works. I would be surprised if that would work on the first attempt, but you never know until you try. So seems like it's reading from somewhere, waiting for something to happen. So let's see what's going on there. Have debugging symbols as usual, so we should be able to debug it. Actually, we didn't have to stop it because we want to see where it's stuck. File Python elf, and since I compiled it locally, we should have all the symbols and everything. Where are we? Ooh. Or maybe not. Oh yeah. Is it continuing to run even though strange. Just run it for a moment without starting the program, so it runs through DB. Right. Yes. Continue. Get all those reads. Not very useful. How did we get into this place? Seems like somewhere in the boot ROM. Yeah. Anyway, if we do this assembly, you can probably see what's going on here. It's probably stuck in some loop where it's reading it's reading from this this address, and this is probably something that doesn't, oh, maybe it's, yeah, it's not 96 hexa, yeah, from this address, and then it compares it to 0, and I think it's 0, then does another read. Let's see if we got this address somewhere. Would SSI base status, yeah, DR0. So we already implement that, but there is another read from 20 and 24, and we don't do that. So we probably need to implement those registers as well. Sure. I1. Where are the registers of this SSI? Registers. TX FIFO level and RX FIFO level. So TXFLR. RX are like I register and their offset, and this is like 4, right? 20, 24. Then reading from them, let's just see what they should probably return 0, that value. Let's try that. TXFLR 0 and the RX probably telling us nothing to transmit and receive. I think the default, like if we don't have any value, is to return F. So that's probably, yeah, why it's failing, because it's getting this invalid value. So let's try to restart and see what's going on. Get any further now. Running, yep. Okay, so now it's somewhere, we don't know where, but we can figure out with GDB. Where are we? Yes, flash do cmd const prop in flash get unique ID. Probably something. Have sources for this? No sources available. Bummer. Yeah, but it's probably also reading from the flash. Seems to load something, then yeah, it seems to read from value plus 40. So yeah, I think we have this. I think we already in this address 28 into the SSI. That's SSI base plus, yeah, SR status register. So right now we are returning this value 4. Maybe it expects something else here. Yeah, and at some point we'll probably have to implement SSI probably those. Yes, want to say that either transmit FIFO not full should be true. I mean, probably waiting to transmit something. Let's see. It loads. Where are we? Loads this value into R0. Then we have 4 because that's what we return, and then it bitwise ends it with, yeah, it checks this bit 8. So 8 is like RF and E. So it probably expect this ISR RF and it probably expects this to be true as well. R E B 8. Yeah. Now let's see if this is happier, or we made it past this test. Okay, starting GB. Where are we? Still in the same place. Okay. Yeah. This part that we are reading. Okay, this is where we are reading. And we got 8. Shouldn't we have like wait a second, something is strange here. Did we get 8? We should have like this twice or. Why did we go from here to there? First of all, for that, yeah, it seems like we returned the right thing, bitwise or between this. Something strange with the flow of the code. Maybe we can find a source code for this. Let's do CMD. See? Okay. Oh yeah, this probably this function. So yeah, it seems like it's looking at TF and F as well, which is 2. So let's try to set that one. Probably easier. Figure it out from the source code as well. So TF and F. Transmit not full probably. TF and F. TF and F is 2. All right, let's see if this helped to pass this test in MicroPython, or are we still stuck there? Ooh, yeah, we got further. Now we are reading from RDC base, read from C. What's this RDC base? Probably the RTC and registers. What is C? Control. Probably, I think it would make sense to take a look. Where are we reading from it? So figure out what to expect. Yes, where? RTC running. Wonder, we probably should have compiled with better debugging symbols, because it seems like we haven't, but very tough. RTC running doing is just implementation. It's checking for this register, so we probably should crawl another one. See, and for now we should just return this value when reading from this scroll register. Was URL. L equals C. Then we are reading from RDC CRL, then just return the value. I think it was 2, right? That's what the expects. Yeah. Let's go RTC access. Just return this and see makes if it makes this happy and continue. We also need to do RP2040 peripherals and load this RTC somewhere. Here we go, RTC base. So new RP2040 C. All right, let's try that again. Running MicroPython maybe. Ooh. Now it's stuck in another place. Okay. Where? Still in RTC running? I think we fixed that. I mean, we don't get this error anymore. RTC set date time. Let's see. It expects it to return false. Solid. Yeah. While RTC is running, it just does nothing. Oh, so yeah, it writes there 0. It expects it to go inactive. Then it writes their value and it expects it to go active. So that's the logic we should implement. Where is RTC? So running false, let's say true, then write unit to number, then say super.write, that's default offset value number, and then switch offset old case RTCCL running is value probably better check sheet. It's just a quick way to get this just past the code test, but it's probably not a correct indentation. Otherwise 0. Just make it happy. That helped get past this busy wait loop. Where are we now? Yes, go on, you can do it. Okay, I think it went further ahead because we have all those writes. Where are we? Yeah, it seems to be again in the boot ROM. Yeah. Probably. Seems like it's trying to write outside the RAM, so probably an issue here. Yeah, anyways, we sort of managed to get MicroPython a bit, don't know where, but it's now said that we don't have those. Who called us some memory? Probably not gonna work. Let's see, finish. Yeah, GDB doesn't figure out where we are because we are somewhere in the boot ROM and gets confused. But yeah, so I think we have done some progress towards getting this MicroPython to run. Probably changes, so sign off with that. I don't know, there might be one more issue blocking us with getting MicroPython to run, or there might be multiple. One thing we can probably do just to get some estimate is just at a breakpoint. Restart it's the breakpoint RDC function that we know visited before. We will call that here. Break here. Continue. Okay, where are we? We are inside the main. Nice. One. SM. So yeah, you can see there is like this main, and open MicroPython. Good. Find who calls this RTC at a time inside MicroPython. Yeah, like the main of the RP2040. So we got this far at least, and then there is like we probably die somewhere down the road, but it's not too bad. Like we got past this finish, we probably turns to main, and then just run a few more instructions to see it gets past this one, past this one, past that limit, and yeah, it seems to die inside here, somewhere inside GC init. Probably some bug here, all those undefined address rights. So yeah, that could be fun to debug with gdbdiff now that we know where it happens, or we can probably I can probably recompile it with debugging symbols, so we don't have to step to assembly, but we can go through the source code and see if we can figure out where it gets stuck. Yeah, so we got some nice progress getting it to run. Still not there. Maybe in the next live stream or spontaneous live stream, we'll see. Anyway, I'm really happy we didn't have any kind of sirens or interruptions during this stream. Let's just commit this bunch of changes. Worry about, no, it seems good. The toy station plus there's Python start. Yeah, still haven't got running MicroPython, but we are a few steps ahead. For signing off, see if our hello UART still runs. If interfere with that with all our fixes, and who happened here? Oh, indeed, hello UART. So underscore you can probably just convert so original file without the change in it, loading the original. Yeah, hello UART. So cool. So to finish this stream happily, let's just release a new version with all those fixes. We have so many fixes here, so we must celebrate that with the release. And yeah, thank you for joining me for this bug squashing and trying to get MicroPython to run. If you feel like getting it, trying it yourself, like you know how to do the bug squashing, and if you feel like compiling MicroPython yourself, just to try to get past the point where we got in this GC init, then there is like those instructions here how to compile to download and compile MicroPython. It's super easy, like just typing a few commands and you have everything here. And also how to enable here. This is like what you need to change, where you need to change to enable the UART REPL. That's what I did. You know, if you need any help, you can ping me. So posted the link to the chat in case anybody wants to try. And yes, good. Our new files, and we're good with that. Like a bug fix release, we haven't really added any significant features, though pretty sure that in the next live session on Tuesday we will add list alarms for timers, because we need them for the next class in the Pi Pico course. And yeah, I will keep waiting for this release. It will take a few yeah, hope I'm not running it in the same terminal where I have this environment set to test against the actual, or yeah, I think I probably have, because the test have failed. Anyway, I will yeah, probably if I open a new terminal and run npm test, then all is fine, I hope. No, we have one failing test. Ooh, a bummer. One which failing test. At a test filter, probably. That's why we didn't notice that. Test for our 5. Yeah. Yes. Like test we had before, and now it fails. Set PC R5 0 step in and carry. Probably lucky that we have tests that run before the release just to find out those ones here. Not sure how we missed this before, but focus test fixing one thing and destroying another. Yeah. Register, so probably something to, oh, of course the condition here is incorrect. If shift amount is 32 or less, then we should do this. Otherwise, if more than 32, we should false. Right. Thanks test for catching that. 40 calculation, yes. Now we can happily restart this. Start a new terminal, so any environment variables that filter all pass, great. Okay. Oh, NP. Yeah, anyway, I will now that the tests pass, I will just do the release offline. Need to keep you waiting. This has been a long session, and thank you all for joining me for, I think it's already approaching 3 hours and 30 minutes. That was long. We squashed a lot of bugs. I hope you find it interesting. As usual, you're more than invited to contribute and connect on Discord. And if you have any questions, I'm there, or suggestions, and also leave open pull requests or issues on GitHub if you feel like. And I hope to see you again on Tuesday. I hope the situation here improves. No more sirens, alarms, and rockets, and we can calmly continue with the weekly live coding episodes. Emulator. So until then, have a great weekend, and see you again. I really hope on Tuesday. Bye bye.